So we'll just do the homework part of section 5.1. You need to do all the odds in most of chapter 5. I really kind of streamlined the chapter, so there's going to be less problems that we're throwing out. So let me just jump into it. And I kind of wrote the rules down that I was going to use just to get us used to integrating. So problem 2, which is our first homework problem that I'm going to do, I need to rewrite this so I can add 1 to the exponent and divide by the new exponent. That coefficient of 2 I'm going to bring out front, leave everything intact. So that's using the rule, the property of logarithms that allows us to pass a constant and make it a coefficient. And now I'm ready to integrate because I just have a generic x to some power. The exponent's not -1, so I'm going to add 1 to the exponent, multiply by a fraction that has 1 in the numerator and the new exponent in the denominator. The new exponent's going to be 4 when I add 3 and when I get 4. So that's using the rule, add 1 to the exponent, multiply by a fraction with 1 over the new exponent, and then my plus c. And now just reduce. There's going to be a lot of fractions in this chapter that are just unavoidable because of this fraction part of the integrating. So cancel the 4 with the 2. The 2 becomes a 1. The 4 becomes a 2. So really I have here is 1 times 1/2, and anything times 1 is itself. So for an answer, I'm going to get 1/2 and then x to the 4th plus c. Your problem 1 was even nicer because I won't have a fraction answer, but I'll let you do that for homework. There's answers for you to check. Yeah, I was wondering if I could just stack on this and not have to flip pieces of paper every time. Looks like not. So problem 4, same issue as problem 2. I can't integrate with that coefficient, so let me drag that coefficient out front. Make this 1/2 times the integral. I'm going to emphasize x to the first power dx. That's just set up perfectly for the power rule. I'm going to add 1 to the exponent, multiply by a fraction that has 1 in the numerator and the new exponent in the denominator. The new exponent's going to be 2 because I'm going to add 1 to that and get a 2. New exponent is 2. Tack on the plus c. Now this is just multiplying fractions. Multiply the 1's across the numerator, the 2's across the denominator. And I get 1/4 x squared plus c for my answer. Six is just the integral of a constant, so there's no rewriting necessary because that 7 is just a constant. The integrand's a constant. When the integrand's a constant, you just use the integral of a constant rule, meaning you tack on an x. And as I fonted this up, the plus c drifted over there, but I can't forget that plus c. No work, no rewriting for that one. That's the only kind of problem in this section that's not going to need rewriting. Problem 8 is going to need a lot of rewriting. I can't integrate a polynomial, so I'm going to need to use these rules with the adding and subtracting to split the one integration into 3 integrations. And then a couple of the integrals will have coefficients. I'll need to drag those out front. So first, I'm going to create 3 logarithms using the properties of logarithms that say if you have addition or subtraction in the integrand, you can make multiple logarithms, multiple integrals. I don't know why I've got logarithms on my brain. Must be something in college algebra I was doing. So I made multiple integrals, and now I need to pass the coefficients out. So the 4 needs to go in front of its logarithm. That's using this rule that says if I have a coefficient, I can drag it out and precede the integral sign. And then that third integral, that's a constant. I don't need to rewrite it. So split the single integral into multiple integrals using those properties. Made the coefficients out of in front of the integral using that property, Now, for these, I'm going to add 1 to the exponent. That's going to be 5x for its integral. So first integral, I have a 4. I multiply by a fraction that has 1 in the numerator, new exponent, which is going to be 3 plus 1, 4 in the denominator. Make the new exponent 4. Bring down the minus sign and the 3. The new exponent here is going to be 3 because that 2 is going to bump up to 3. So I'm going to multiply this by 1/3. Keep the x, make it correct, make it an x cubed. Last integral is an integral of a constant, and constants integrate to that constant times x, and I always get my plus c. I set this one up really nicely to cancel. 4 times 1/4 is 1, 3 times 1/3 is 1. So both the variables should have coefficients of 1, which I can not write. And so instead of writing 1x to the 4th, I'm going to write just x to the 4th. Instead of writing minus 1 times x cubed, I'm just going to write minus x cubed. And that's plus 5x and plus c. And that's everything. That's the answer to number 8. Fractions are not my friends in integrating. The only way I can integrate a fraction if it's a 1 over x, I can't have a number in the numerator that's not 1. 3 is no good. And that x to the 4th makes it so it's not even a logarithm rule. I need to rewrite this, learning some stuff from algebra. If I have a fraction that's just a monomial in the denominator, I can rewrite the fraction with a negative exponent. This 3 over x to the 4th, I can rewrite it by dragging that x to the 4th up from the denominator, making the problem so it's not a fraction anymore, but it has a negative exponent. So there's a lot of algebra tricks that we're going to have to remember in this chapter, and this is a super common trick in this chapter that's going to come over and over. So I've just rewritten the problem so that it's no longer a fraction. That's a good place. Now this is just x to some power with a coefficient I need to deal with. This exponent doesn't have to be an integer. I prefer it to be an integer, but it can be a fraction, it can be a negative number, to still use the rule of adding 1 to the exponent and multiplying by that fraction with 1 over the new exponent. Before I integrate, I'm going to drag the 3 out front, and now I have this written so it's ready for the power rule. Most of what I'm doing is, for the rest of the section and the rest of the chapter really, is just getting the problems set up so I can apply one of these rules that I have. These are all the rules we're going to get. Power rule, constant rule, ln rule, and e rule. There's only 4 rules that we get in this whole entire chapter. It's the getting the problem ready to use the rule that's not good. So let me figure this out. So what's my new exponent going to be? My new exponent's going to be negative 4 plus 1 when I use the power rule, which is going to be negative 3. So I should multiply by 1 over negative 3. Quite honestly, that's not so friendly for me. I'm going to move that negative up to the numerator and multiply by negative 1 over 3. It makes the algebra a little bit easier to follow. Both of these are equal to negative 0.333 as a decimal. This version is going to be easier to work with. So my new exponent is going to be negative 3. I've integrated. I just had to put the plus c on. Now let me do this simplification. This is where it gets a little bit sketchy. 3 times negative 1/3, the 3's cancel and they become 1s. So this really becomes negative 1x to the negative 3 plus c. And I'm going to do exactly the reverse. I'm going to go from something with a negative exponent and I'm going to turn it into a fraction. Instead of taking the positive exponent away from the denominator, I'm going to move the negative exponent down to the denominator. And so for an answer, I'm going to move that x to the negative 3rd down to the denominator and make it have a positive 3 as an exponent. I'm going to leave the negative 1 in the numerator, because this would turn back into that using that strategy of just sneaking the denominator up to the numerator with making the exponent negative. This only works if there's a monomial. If there's adding or subtracting in the denominator, then this trick doesn't apply. Hopefully this is not feeling horrible. the section that I rewrote, it was kind of ugly. And when I initially wrote all of the material for Math 212, Math 218 was just being developed, and I knew there was going to be calculus in Math 218, so I didn't want to shortchange you on any calculus. Turns out that integration is not in Math 218, so I really lightened up the section so we can focus on the theory, the applications, without really discussing algebra, even though the algebra is not going to be so nice in some of these problems. Problem 12 is more or less the twin of number 10, so I'm just going to rewrite it the same way. I'm going to drag the x cubed out of the denominator, make it have a negative exponent. I'm going to make the coefficient out in front of the integral. Now I'm going to plan out my new exponent. My new exponent is going to be negative 3 plus 1, which is negative 2. And instead of multiplying by 1 over negative 2, I'm going to multiply by negative 1/2. I'm going to stop writing the integral sign. The fraction I'm going to multiply by is negative 1/2. The new exponent on my x is going to be negative 2. I'm not going to forget the plus c, although I'll forget it all the time when I'm writing keys. Now these fractions I set up real nicely. All the time in this chapter, we're going to wind up with fraction answers. They're kind of unavoidable. But this one won't be so much. Well, it'll be a fraction because when I turn the negative exponent back into a positive exponent, I get a fraction. But the coefficient won't be a fraction. So for the coefficient, I'm going to get 4, fraction gone, times negative 1, which is negative 4, x to the negative 2, plus c. And now I'm just going to create my fraction, bring the x down to the denominator, leave the negative 4 up in the numerator, and that's going to be my answer to problem 12. For me, these don't feel horrible, but I've started doing this 40 years ago, and maybe that just has something to do with it. I'm just so familiar with them. I can't integrate when there's multiplication, just like that example I did in part 1. So let me get rid of the multiplication by going 4x times x cubed, and then 4x times 3x, and then 4x times minus 4. So rewriting it by clearing the parentheses, I usually put the whole polynomial in a parentheses, but it's hardly that big of a deal. First multiplication would be 4x to the 4th. Second multiplication is going to be 12x squared. Last multiplication is going to be minus 16x. You should start skipping steps if you can. Rather than doing every single step that I'm showing, you might be able to figure out how you can skip a step or two and still get the answer. That's a good idea. But you don't have to. I think it's not, some of these steps are pretty easy to combine together, but I'll do them one at a time just in case you need it. So now I have a polynomial. I use the adding and subtracting rules to make this into multiple integrals. Should write equals. Anytime I write something that's equal to the line above it, writing equals is good. For each of my integrals that has the coefficients, I'm going to drag the coefficient out front. This should have been 16x. I forgot to write the x there. So this should be minus 16 times the integral of x dx. And that x has an exponent of 1. So I need to plan out my new exponent so I know what to multiply by. So first coefficient of 4 is going to be multiplied by 1 over 5 because the new exponent is going to be 5 when I add 1 to the 4. Bring down my plus sign. After the 12, I'm going to get a 1/3 because that x squared, when I add 1 to the exponent, is going to become an x cubed. In the 16, that exponent was 1, so the new exponent is going to be 2. I need to multiply it by 1/2. Don't forget my plus c, which I always forget. And now, This first 4 doesn't cancel with the 5, so I think of it as 4 over 1 times 1 over 5. I'll multiply 4 times 1 and get 4, multiply 1 times 5 and get 5, and leave my x to the 5th. Second multiplication, good things happen. This 12 and this 3 cancels. The 12 cancels into a 4. The fraction goes away. I'm left with 4 times 1, which is 4, and then the x cubed. Third, also canceling. 16 cancels with the 2. The 2 becomes a 1. The 16 becomes an 8. Technically, I have negative 8 times 1 x squared. That's going to give me a negative 8x squared. And I still have the plus c tagging along. And everything for 14. Didn't do one like this in the examples, but I still can do these. Problems 15 and 16, they have multiplication in hiding. I can't even split this into 2 logarithms right yet because of the squaring. I need to do the exponents first. So for this problem, to get it so that I can apply the only few rules that I know for integration, I need to rewrite it without the exponent, showing it as repeated multiplication, and then I'm going to do the foiling. The firsts are going to be 2x times 2x. The outers are going to be 2x times 5. The inners are going to be 5 times 2x. The lasts are going to be 5 times 5. When I do the foiling, the 2x times 2x is 4x squared. Both of the 2x times 5x's are both 10x's. I'll add those to get a 20x. The 5 times 5 is a 25. Now I've gotten rid of the multiplication. I can't have multiplication with variables when I integrate. And now let me skip a step. I'm going to write 3 integrals, and I'm going to write the coefficient. So my first integral, rather than making it 4x squared with the 4 inside the integration sign and then moving it out, I'm just going to move it out right on the first step. For the second integral, I'm going to keep the 20 in front and the x under. And my third doesn't have a variable, so I'm going to make the whole 25 stay under. So I just skipped a step. I did 2 rules in once. I did the adding rule to split the single integral into multiple integrals, and I snuck the coefficients out just to be efficient. And now I'm going to integrate. That coefficient of 4 is going to be multiplied by 1/3 because the new exponent 2 is going to turn to 3. The coefficient of 20 is going to be multiplied by 1/2 because the exponent started at 1. My new exponent is going to be 2 when I add 1 to it. And the third is an integral of a constant, and a constant, you just get that constant times x. First multiplication, nothing cancels, so I just go 4 times 1 and get 4/3. Leave the x cubed. Second cancels, the 20 cancels with the 2, and you get 10 and 1. That gives me a plus 10x squared. Still have the plus 25x. Still have the plus c. And notice I'm not really factoring these. The c makes it so factoring doesn't even make sense because it doesn't even have the x. So I'm just getting the integral and just kind of stopping. So that would be a perfect answer for problem 16. Your problem 15 should work similarly. Same deal for 18. I can't integrate that the way it's written, so I need to get rid of the parentheses. It's another foiling problem. It's a more obvious foiling problem. The foiling part of 18 would be doing x times x, x times 7, minus 4 times x, and minus 4 times 7. So the rewriting of this, the x times x is going to give me an x squared. And then the x times 7 is a 7x, the minus 4 times x is minus 4x. Those will combine to be a positive 3x. The minus 4 times 7 is minus 28. Should write equals because this equals to the line above it. Now I'm going to write 3 integrals, bring the 3 out front of the middle integral. So I'm going to make the first integral x squared dx. The second integral, 3 x dx. And the 28 stays inside because it's a constant, then minus 28 dx. First one, the new exponent's going to be 3. I need to multiply by a fraction that has 1 over the new exponent. So the first integral is going to have a 1/3. Doesn't have a coefficient to start that I need to worry about, but it's going to be 1/3 x cubed. Second one has a coefficient of 3. It has an exponent of 1 that's going to turn to 2, so I'm going to multiply by 1/2 and get an x squared. The last integral is a constant, so you just tack on an x. And I try not to forget the plus c, but I forget it frequently. Nothing's really going to simplify here. This multiplication, I think of it here as 3 over 1 times 1 over 2 and get 3 halves. For an answer, I'm going to get 1/3 x cubed, and then 3 times 1 and 1 times 2 is 3 halves x squared minus 28x plus c. (19) and 20 have fractions. I need to get rid of the fractions. These are easy fractions to get rid of because the denominator doesn't have pluses or minuses. Section 5.2, we get denominators with pluses and minuses, and then it's a whole mess to figure out what to do. But I've got to get these things rewritten. I can't have anything but individual terms that I could separate into individual integrals. So I rewrote the single fraction as two fractions. The first fraction, 4x squared over x, I could cancel out the denominator x with one of the two x's from the x squareds. And that first term is just going to be a 4x. The second fraction is not even going to be a fraction. The x's are going to cancel. I'm just going to get a 5. Now I can write two individual logarithms. I'm going to write the 4 in front of the first logarithm. So I'm going to write 4 integral. I don't know why I keep saying, I don't know why I got logarithms on my brain. 4 times the integral of x dx plus the integral of 5 dx. The 5 stays inside because it's a constant. This integral, I'm going to add 1 to the exponent. The exponent was 1. The new exponent's going to be 2. So this is going to be 4 times 1/2 and then x squared. Second integral is a constant, so it's just that constant 5 times x. And then my plus c. Cancel this 4 with that 2. Fraction goes away. 4 divided by 2 is 2. This gives me 2x squared plus 5x plus c for my answer. E's are nice. They're the easiest rewrites. When I have an e, the only e I can integrate is e to the x power. For this one, I'm going to get it rewritten with e to the x power by making the coefficient out in front of the integral. And now I'm going to apply the e rule. The integral of e to the x power is just e to the x power, of course, plus c. And the 6 that's in front is going to be multiplied by that integral. But the plus c I usually just tag off to the side. Technically, I could have said times 6c, but because this represents any number, 6 times any number is just any number, usually we never multiply the c's by the coefficient. So this integral turns to e to the x, but I needed to multiply by the coefficient, because this really turns into e to the x plus c, so this is going to be 6 times e to the x plus c. 24, exactly the same. 23, exactly the same. Even though it looks more impressive, it's not. I'm just going to drag the coefficient out front so I can use the e rule. The e rule doesn't have coefficients. The exponent just has to be a single x, and there can't be a coefficient. If that's the case, the integral is just e to the x, and I can't forget about the coefficient. I just tack it on after I do the e integration, throw the c at the end. So 24, it's going to be negative 4/5 e to the x plus c. I didn't do the ln examples in the first part of this video. I didn't really like the way I wrote it up, so I purposely skipped over those, but we can do those now. So how am I going to integrate this? It's a fraction. I don't integrate fractions so well unless they're 1 over x. 3 over x isn't quite 1 over x, so let me get this rewritten. I think of this problem as 3 over x to the first power dx. And I'm going to use that same strategy that I used for the other fractions that had just a single term in the numerator and the denominator. I'm going to rewrite it with a negative exponent. And the negative exponent version of this is going to have a negative 1 exponent. And negative 1 exponents turn into ln's. But I can't integrate anytime I have a coefficient. I always need to pass that coefficient out front. When you have a negative 1 exponent, you don't use the add 1 to the exponent, divide by the new exponent. You use the ln rule. So this is going to be 3 times the natural log. Technically, you need absolute values. Realistically, I wouldn't take points off if you didn't do them. It's a domain issue. This domain is all real numbers except 0. This is domain of all real numbers bigger than 0. You want the domains to match as much as anything. So that's 26. Getting close to the end of this section. 28 is really just the same as 26. The fact that the numerator is a negative number doesn't impact at all the integrating. I'm going to rewrite it the same way. I'm going to make it the integral of negative 2x to the negative 1 power dx. Now pass the negative 2 outside and make it a coefficient. And use the rule if my exponent is a negative 1. This ln rule, if you have x to the negative 1 power, its integral is the natural log of x. I'm going to leave the coefficient in front of that natural log, give it the absolute value, tack on my plus c, and that's how we'd write the integral for problem 28. Just 2 more problems. You need to get real comfortable with this section before you plow into section 5.2, because these rules come back again, but the rewriting in this section, not so bad. The rewriting in section 5.2, that's the hardest section that I think that we do, because the rewriting is something that doesn't even feel legal at first. I remember learning what we learned in 5.2. I'm like, that can't be allowed, but yet it is. 30, I'm just going to pass the 2 out front. Can't have coefficients before I integrate. Now it's just an x to the negative 1 power. X to the negative 1x to the negative 1 power is just a natural log. So this is going to be 2 times the natural log of the absolute value of x. Tack on my plus c. And then 31 and 32, same. Just I don't even think I wrote too many of these, but sometimes I don't have enough of a single kind. I want to make sure to at least have a couple. So even though these are pathetically easy, recognizing which rule to use is not so easy. So when I see an x with an exponent, if it's not negative 1, I add 1 to the exponent, multiply by that fraction with 1 over the new exponent. X with a negative 1 exponent, you get a natural log. The coefficient gets multiplied by the natural log, and I keep that plus c. So that's everything for 5.1. Again, really let this digest before you plow on to 5.2. You need to really be comfortable with these basic rules of integrating and a little bit the rewriting, but we're going to learn a new rewriting technique that will apply as the problems get more complicated in section 5.2.